All right. We're going to look at a house calculation on figuring out what the service conductors coming into the house and into the panel need to be sized to according to the Canadian Electrical Code. So we're going to be looking at Section 8, Circuit Loading and Demand Factors. So in electrical, we talk about demand factors. So in particular in homes, when we're trying to figure out how to size the conductors going into a house, we need to account for what that demand, the amount of that current or electricity is going to be needed for that house. And there's a certain way of going about that. And you do demand factors for other things like motors and transformers and for ranges and stuff like that. But the reason we do it is if you think about a house, you don't necessarily have all the loads on the house on at the same time. You're never going to be using that maximum amount of current. So there's a bunch of rules that outline how you come up with a particular number, a demand, a wattage of what that house is going to need. For instance, you're not going to have all your heat cranked up in your house at 100% in every single room, have the range on full blast, along with the air conditioner. It just doesn't really make sense. So that's what Section 8 deals with, demand factors of certain things. And in particular, 8-200 is what we're going to be looking at, which deals with single dwellings. So homes and townhomes and stuff like that. All right. So we're going to tackle this question here, a single dwelling demand calculation. We're dealing with 120 240 volts, 3-wire system, overhead consumer service conductors, and which are rated at 600 volts and rated without jacket. And we need to keep in mind that all termination points are going to be rated at 75 degrees Celsius. And we're given this information here. So we're given a particular amount of area that this house is. And that's how we generally figure out what the wattage demand is for like all our lights and receptacles and stuff like that. We don't actually count up all the receptacles. We deal with square footage or square meters and figure out approximately how many receptacles you would need, how many lights you would need for that particular area, and how often they're going to be on and used. Okay, so let's take a look at the code rule. So the calculated load for the service or feeder supplying a single dwelling house, so the conductors coming into your panel, shall be based on the greater of item A or B. So item A here includes all of this here. So we're taking a look at a bunch of the loads in a particular house and coming up with a wattage that relates to all those loads. But we need to keep in mind item B. So item B states that you're going to take 24,000 watts where the floor area exclusive of the basement floor area is 80 meters squared. So if you remember our question here, our main floor is 95 meters squared. So that is greater than the 80 meters squared that the code rule takes a look at. So we're going to take 24,000 watts, or the wattage calculated in item A, depending on, we're going to take the largest wattage. So the first thing we got to do is figure out how many watts we calculate in item A and see if it is indeed larger than 24,000 watts. So the first thing we're going to take a look at is calculate how many watts for the living space that we have. So we have 60 meters squared for the basement. Now, if we take a look back at the rule, it says a basic 5,000 watts for the first 90 meters of living area. So we got to see Rule 8-110. Whenever it says see a rule, see the rule. So 8-110 says 100% of the area on the ground floor. So level 1, 100% of any areas above the ground floor, level 2, level 3, etc. And 75% of the area below the ground. So the basement, we're only going to take 75% of that. And that's because the basement, you're not necessarily going to be living in there very often. And so you don't have to take as much of a demand factor, as much of a demand. So you're only going to take that at 75%. So we're going to multiply that by 0.75, and that gives us 45 meters squared. Now, the main area we're going to take at 100%. So 95 meters squared times 1, representing 100%. That's going to give us 95 meters. If we add those together, that gives us 140 meters. So if you remember the rule, it says we're going to take 5,000 watts for the first 90 meters. So 90 meters squared goes into 140 meters squared, 1 with 50 meters squared left over. So we're going to take 5,000 watts for the first 90 meters. And then any portion thereafter, so this 50 meters squared, we're going to take that at 1,000 watts. Right? So our total area, we're going to account 6,000 watts to. Now we have our gas furnace. So gas doesn't use electricity. You might need a plug for the pilot light, whatever, but that takes very minimal amount of current, so we're not even going to bother with that. The range, however, we will be. So let's go back to our rule. And item 4, any electric range load provided for as follows: 6,000 watts for a single range. So we have a electric range, we're going to take it at 6,000 watts. But it also says plus 40% of any amount which the rating of the range exceeds 12 kilowatts. So our range exceeds 12 kilowatts by 4,000 watts. It's a 16 kilowatt range. So we're going to take that 4,000 at 40%. So we got 6,000 just because we have an electric range, plus the extra 4,000 at 40%. And that's going to give us 7,200 watts. So our range is accounted for 7,200 watts. Then we have our dryer at 5,000 watts. If we go to item 7, any loads provided for that have a rating in excess of 1,500 watts, so this dryer would be included, in addition to those outlined in items 1 to 6, at 25% of the rating of each load if an electric range has been provided for it. So in our case, an electric range, rather than a gas range, has been provided for. So we're going to take that dryer at 25%. So it's 5,000 times 0.25, which is going to give us 1,250 watts. So dryer equals 1,250. If we add those all up, we get 14,850 watts. That's what we calculate. But if you remember, we got to take the greater of item A or B. And item B, because again, our main floor area is greater than 80 meters squared, we're going to take that 24,000 watts rather than our 14,850 watts. Okay. So we're taking the greater of the two. And if you remember Watt's law, so power equals current times our voltage, we can figure out pretty quickly what current we're going to need for this particular service. So we know that we have 240 volts coming in. So if we want to find our current, current's going to equal power over voltage. And that's going to give us a total of 100 amps. Okay. So our calculated amperage is going to be 100. Now we got to figure out what size conductors we're going to need for that 100 amps that is demanded by that house. So to figure out ampacity of conductors, we turn to table 1 to 4. And because we're dealing with copper, and we know that a service has to go through conduit or a cable, we're going to be dealing with table 2. So table 2 is going to be allowable ampacities for not more than 3 insulated copper conductors rated not more than 5,000 volts and unshielded in raceways or cable. So key word there being copper and a raceway and or cable. So we're going to use this chart, but we got to keep in mind that though we're dealing with R90 XLPE conductors, our terminations are going to be rated at 75 degrees, maximum 75 degrees. So when we're looking at our chart, we got to actually take from the lowest common denominator, from the lowest temperature rating. So it doesn't matter that our conductors are rated for 90 degrees. We need to take what those termination points that those conductors are going to. We're going to take that temperature rating. So we're reading from this column here. And if you see, we're dealing with 100 amps, and that's going to be size 3 conductor for copper. So we can fill that in. Number 3, and that was good for 100 amps. Now we want to go and figure out what it is for aluminum. So if we go over to table 4, that's going to deal with aluminum conductors going through a raceway. We're looking at the 75 degree column, and we need an ampacity of at least 100 amps. So we're going to take the minimum, which is number 1 AWG conductor. So let's fill that in, number 1, and that's good for 100 amps as well. Okay, now we got to figure out what the maximum size breaker for the main service is. So to find out a breaker size, we go to table 13. Table 13, rating or setting of overcurrent devices protecting conductors. And we're looking for the ampacity of the conductor. So if you remember, the ampacity of both number 3 and number 1 aluminum and copper respectively was 100. So we need a rating or setting permitted for our overcurrent device, our breaker, at 100 as well. So let's fill that in. So we're going to have a 100 amp breaker, and that was found at table 13. Minimum size copper grounding conductor to connect to the main service ground if the following electrode is used. So this is a bit of a trick question because our ground conductor is always going to be sized at number 6. Always. So we can fill that in, and it doesn't matter what the particular electrode used is, whether it is a plate, a UFR, or an in situ, it's always going to be number 6. And the rule we look at for that is going to be 10-114 subrule 1. And that indicates that we always need a number 6. Now, minimum size field assembly electrode, or a UFR, is going to be basically, instead of using ground rods or a ground plate, you actually use a bunch of conductor, a piece of conductor, and lay that in like a footing of the building, and that conductor is gonna act as your ground. So you gotta size that UFER, or the field assembled electrode, according to table 43. All right. So if we go to table 43, let's see here. So minimum conductor size for concrete encased electrodes, that's going to be, again, our UFER. Ampacity of largest service conductor, or equivalent, so that's going to be 100. So here, 165 or less, we're going to need a number 4 copper UFER. So number 4. And that rule is going to be 10-102. Okay, minimum panel size. So that, when you talk about panel circuit size, that's how many breaker spots in that particular panel. And so for this one, you're going to be going to 8-108. Oops. 8-108. Number of branch circuit positions. So the one we're looking at is 24, of which at least half shall be double pole, where the required ampacity of the service or feeder conductors exceeds 60 amps but does not exceed 100 amps. So we fit in right there. 24. So 8-108 subrule 1B. Uh, 24. Minimum size of mast for the overhead service. So services are going to be in section 6. And the rule that we're looking at in particular is 6-112 subrule 6. And that's going to indicate that a mast always has to be trade size 63. So let's just take a look at that real quick. Ooh. 6-112. A rigid steel conduit of a minimum nominal size of 63 trade size shall be permitted to be used for purposes of subrule 5, provided that all the requirements of the service mass are complied with. Where service mass are used, they shall be in metal and assembled from components suitable for a service mass. So this indicates that trade size 63 is appropriate, and that's going to be 2.5 inches in diameter. Minimum size of service conduit for the overhead services. So this is going to be the conduit that comes down the side of your house and then eventually elbows into the house or into the meter. So we want to take a look, because all our conductors are of the same size. We're going to look at table 6A. So let's take a look at that. And because it indicated in the question here that we're dealing with 600 volt insulation and we're dealing with thermoset R90 conductor, this is the table we're going to be using, as opposed to there's 6B, 6C that deals with other insulation ratings. But 6A is what works for us. So you got to make sure you got the right one. And it is... Well, we're dealing with, for copper, we're dealing with number 3. And to get 3 in there, so we got line 1, line 2 in our neutral, because we're dealing with a 3-wire circuit, we're going to need trade size 27. So we can indicate that by trade diameter 27. And for aluminum, 27 is going to be 1 inch. For aluminum, we're using number 1. And so to fit 3 in there, we're going to need trade size 35. And that is also found in 6A. And there you have it. That's how you do a house calculation. And figure out the corresponding breaker size and conduit size and stuff like that you would need for that particular service after you figured out the size of the conductor. So hopefully that helps, and let me know if you have any questions.